All right, thanks very much. So yes, I'm Cody Doucette. I'm here today to share with you an architectural approach for mitigating next generation denial of service attacks. Just a quick note before we begin, this is being recorded. It's really only capturing the speaker and my slides, so me, but just so you know that if you speak, it'll be recorded. So I don't think it's any surprise to most people in the room that DDoS attacks are a huge problem. Repeatedly and consistently, surveys of network operators show that DDoS attacks are one of their top operational concerns. And if you look at it by the numbers, it's pretty clear why. Peak attack magnitude has been growing exponentially sort of year after year. Google recently released this nice chart which shows, no matter which way you square it, bits per second, packets per second, or requests per second, these sorts of attacks are growing exponentially. Additionally, there's some major social impacts that happen as a consequence of DDoS attacks as well. There's been a huge increase in attacks since the pandemic started with the shift of everyone working from home. There was a high-profile Telegram attack that was blamed on China during the Hong Kong protests last year. So it's really pervading different aspects of our lives. But even with that context, what if I told you that it could get worse? Right? So what if I told you an attack could occur without any attack traffic reaching your servers or services? It could be achieved using low intensity, legitimate looking traffic. And really to stop it, you would have to collaborate with other networks. So in other words, you don't really know that it's happening, except for the lack of traffic coming in. You can't figure out who it's coming from, and you can't stop it, at least not by yourself. And this is actually a well-known class of attack. It's called a large-scale link attack. And this was first introduced, or one of the first pieces of work to introduce this was Crossfire back in 2013. And the general idea is that you can have a massively distributed set of bots that are sending low-rate, legitimate-looking, TCP, HTTP traffic to a set of decoy servers around a target area. So that target area could be an institution, it could be a state, it could be the entire East Coast of the United States. But the effect of this is that with all of this low-rate legitimate traffic, you're getting these certain aggregation points or these target links that are being overwhelmed as a consequence. And these target links are outside of the administrative control of the target area. So you're cutting off service to this target area, and the victim can't really do anything about it because they don't have any visibility into it. And in other pieces of work called this the most devastating and stealthy attack to date. So thinking about whether or not this could actually happen, well, it did happen shortly after it was proposed in the literature. There was a pretty high-profile spam house attack in 2013, where actually the locus of the attack was links coming into an internet exchange point. There was also a Proton mail attack in 2015 that had a very similar flavor to this. So it's definitely possible and can happen, but there are actually 3 new developments in sort of the internet ecosystem that might make these sort of attacks even more commonplace. So we can think of things like increasing botnet scale, right, due to the proliferation of IoT devices. For each one of those bots, they might soon have a greater capacity for these sorts of attacks even due to the rollout of 5G devices and networks. And so at the same time as sort of this aggregate capacity potential is increasing, there's also an increasing vulnerability in the infrastructure due to the transition to IPv6, which is starting to pick up steam. So we can wonder with this confluence of factors whether there's a perfect storm of conditions for a sort of next generation of attacks. And the answer to that is maybe, but let's rewind a little bit and start from the beginning of where our research came from and how we started to tackle this. So we actually started investigating the literature around DDoS attacks. It was 5 years ago now. So our goal was to figure out why now 20 years of academic research into mitigation solutions have largely failed to gain traction in the internet. Okay, so we surveyed all different kinds of architectural techniques and attack detection and how to hold attackers accountable, using different technologies, clouds, for example. And to synthesize all of this long arc of work pretty briefly, we came down to two sort of core findings. First, that DDoS is a fundamentally architectural problem to solve. And in a related manner, full deployability for a DDoS mitigation solution has to be a top priority. It can't just be incremental deployability, right? There's been dozens of these different proposals that have shown the value of an incremental deployment, or how the value of the system grows as more and more networks deploy it. But that's really not been enough to solve the problem, basically. So if we look into why that is, what are the sort of core architectural issues at play that are making DDoS attacks possible and also potent? You could reduce it down to basically 4 issues, maybe more, but there's 4 that I like to pick out. First of all, it's just difficult to forge cooperation between networks, and that's due to the decentralized design of the internet. So when you have attacks, it's generally coming, it's being sourced from a network that's not your own, but you don't have any visibility or control over whether to stop that. It's also just a scale problem, right? It's difficult to defend a single network against the internet scale level of attacks that we've been seeing, right? And that's just owed to the fact that the internet is a massive network of networks. It's also difficult to classify unwanted traffic, and that's due to the fact that the internet was designed as with an open and connectionless network layer, right? With some notable exceptions, you're basically free to send to whatever server or service you want. You might get stopped by a firewall or something along the way, but in general, the principle is open and connectionless. And finally, it's difficult to verify the identities of senders. There's no source address verification mechanism built into the architecture. And that actually drives a lot of the attacks that we see on the internet, especially in terms of like flow state exhaustion attacks. So with all of these architectural issues, there's been a good 20 years worth of these elegant designs and evaluations that show that DDoS is a really solvable problem if only the internet architecture was amenable to it. So instead, the reality of what's happened is that you're getting this DDoS protection market. Your Akamai's, your Cloudflare's, your Imperva's, and this DDoS protection market really only benefits the entities that control significant swaths of the internet infrastructure, right? They're the players that can absorb these attacks when no one else can. And so everyone else, small ISPs, universities, governments, have to pay for this protection. What would be nice is to try to bridge this gap between the research in this field and the reality, right? By focusing as a top level priority on deployability. So that's what we did. So we designed Gatekeeper from the bottom up or top down, however you want to look at it, to bridge this gap between the research and the reality. In other words, to incorporate all of these major lessons learned from decades of research, but to prioritize deployability as the most important aspect. And in order to go along with deployability, to put this thing in reach of a lot of different actors, to keep costs low, but enable scaling up as needed. So yeah, the little guys can deploy it, but also sort of the bigger networks and content providers and larger entities can also use it if they wanted to. So the thesis that I want to share with you is that Gatekeeper is a mitigation system that's going to neutralize some of these architectural issues that make DDoS attacks possible and potent. And that even in the case of those large-scale link attacks, such as Crossfire, and especially because those kind of attacks really take advantage of the architectural issues to the extreme, Gatekeeper can sort of break Crossfire's assumptions and provide mitigating maneuvers to hinder it. And so the three main contributions that we're making here is that we're providing a design, implementation, and evaluation of Gatekeeper, which is actually, to our knowledge, the first open source and fully deployable architectural approach to DDoS mitigation. I'm also providing a Gatekeeper policy toolkit for network operators. So this is going to describe the basic and also some more advanced techniques that showcase the richness of policy programs. Right? These are the things that govern Gatekeeper's usage, that determine whether and how much traffic is going to be able to be sent. And finally, a cloud and internet path measurement study that shows Gatekeeper and certain policy techniques may be able to combat those large-scale link attacks, which is an as of yet unsolved problem. Okay, so that's sort of the background and the thesis. And then the remainder of the talk is going to hit on those three big items. So sort of the crux of what we're going to use to cut through these architectural issues is vantage points, what we're calling vantage points. So vantage points to us are well-provisioned in geographically distributed locations throughout the internet. Their basic requirements are just that they need to have some sort of computing capacity, right? It's not going to be enough to just have routers and sort of static declarative rules to help us fight this problem. We need some sort of computing capacity. These vantage points need to have cheap ingress bandwidth, or ideally free ingress bandwidth. Right? There's going to be a lot of traffic flowing through these vantage points as a consequence of the problem at hand. So we don't want to give the attacker a lever on how much we're paying just to be able to use these vantage points. They need to be able to support BGP sessions, BGP peering, because what we're going to do is we're going to create an overlay of these vantage points such that an Anycast network is created so that no matter where you are on the internet, whenever you try to transmit packets to the destination AS here, you're going to be first forwarded through one of these vantage points, right? So these vantage points are going to announce the prefixes of the destination AS. And so client traffic will first be Anycast to the nearest one. And finally, the last requirement is just private links to the protected AS. Right? If we expose the links between the vantage point and the destination AS, then those could become the subject of an attack themselves. So some examples of these vantage points, the primary one that our deployments are focused on is internet exchange points, but they could also be things like private interconnects or peering links. Some cloud providers also provide all four of these requirements. And so what's going to happen is the deploying AS is going to actually deploy some network gear, or in the case of cloud, some instances inside of these vantage points that are maintained and controlled by the destination AS. So that when client traffic is to be sent to the destination AS, it's forwarded to the closest VP. And that's where the Gatekeeper servers come in. So you can think of the Gatekeeper services, the Gatekeeper servers, as sort of upstream policy enforcement. So their responsibilities are, when new flows come in, forwarding those first packets of a new flow as a request to the destination AS, because that's where a decision is going to be made whether to allow this flow to continue. And for all other flows that we already know about, that a decision has already been made about, we can drop the flows at this point or rate limit them according to some policy enforcement program. In order to send packets from this vantage point all the way to the destination AS and keep that channel private, and for a couple other reasons too, we encapsulate the traffic in an IP header. So that packet is going to flow all the way to the destination AS, where it's going to first be received by a grantor server. So these are sort of the two different ends of the architecture. Gatekeeper servers up front and grantor servers deployed in the destination AS. And the responsibilities of these grantor servers are to make policy decisions about requests that they received for new flows, using those policy decisions by installing them in Gatekeeper servers, right? Telling Gatekeeper, drop this flow, rate limit this flow to this degree, et cetera. And for granted traffic that is allowed to make its way to the destination AS, simply decapsulating it and sending it to the destination server. So these three components, the vantage points, the gatekeeper servers, and the grantor servers, make up what has been defined in the literature as a network capability system. In other words, senders need to obtain explicit permission to send traffic. Right? By default, they're going to be stopped at the gatekeeper server until a decision can be made. Another way of saying this is that we're enforcing a connection-oriented network layer, which to this point hasn't really been available or feasible on the internet. So any questions about this architecture?
Cody, clarification, I guess. So this is these VP vantage points will be there to handle or protect all potential destination ASs, right? Is that correct?
Sorry.
So how many client server kind of interactions you can handle here? I mean, are you thinking of you have an overlay for each application or each
I see. Yeah.
Region, I guess. I don't know what. I mean, is this one overlay for the whole internet?
Yeah, so the deploying AS is going to pick the prefixes that they want to announce, right? The prefixes that represent the services that they want to protect, and then all client traffic that's for those, the addresses in those prefixes, those services are through the vantage points. And in most cases, it would be maybe all of your relevant prefixes, right? All of your publicly addressable prefixes.
And all clients, all senders, how would you force traffic from all clients to go to these closest VP?
It's because
how you do redirect them to this closest VP. That's
using BGP prefix announcements. So the destination AS itself is not the announcer anymore. Each VP individually is.
Okay.
And could you say a bit more about the connection-oriented being at the network layer? Why is it at the network layer?
It's because, in general, the network layer is going to deliver your packets just host to host, right? It's not.
So it's connection-oriented in the same way mobile IP solutions would have been connection-oriented, right? Going through like a.
You have to first reserve or obtain permission to be able to just do that basic host-to-host interaction. Yeah.
Okay, I see.
And Cody, can you just remind me how the addressing works between the VP and the destination AS again? How do you prevent that path from being attacked?
So yeah, this path to the destination AS has to be it can't have exposed globally routable addresses. So you could either hide them via tunneling or via actual fiber, like private links, most likely via tunneling.
Just trying to. So when you say via tunneling, how do you do tunneling without a globally routable IP address? Do you, or
I just mean that they might be globally routable. It's just that the traffic from the client would first have to go through the VP anyway, so you can't directly attack these links.
yeah, I understand MPLS as an example, but those routers still have IP addresses, and you can still DDoS those routers. But anyway, I mean, I take your point, but it's somehow it's hardened. Looks like it's got to be hardened somehow. Either it's a physically hardened, or you've got I don't know. Okay. Anyway, it's all right. Go ahead.
Okay. So coming back up a level and thinking about why this approach solves some of these issues. When we talk about whether it's difficult to forge cooperation between networks, well, we're kind of circumventing that issue, right? We don't need to be requesting source networks to shut off certain flows, right? We're placing our mitigation system upstream in these vantage points that are typically pretty close to source networks, right? In a global deployment where you have many of these VPs, you're getting as close to the source networks as possible without crossing trust boundaries. In terms of just the sheer scalability of the internet, you're making the mitigation system itself distributed and scalable. Of course, we're doing away with sort of the open and connectionless network layer by using network capabilities that are governed by these expressive policies. So in that way, we can determine what's wanted and what's not, and to rate limit or entirely drop flows that we don't want to allow. And this last topic we won't really get into in this presentation, but that's in the thesis, is it's still a difficult problem to verify sender identity. But when you use an architecture like this, you can define policies that are going to take advantage of the fact that we have these kind of insertion points upstream so that we can see where traffic is coming in from and use that data to try to figure out whether or not a flow has a spoofed source address. So we set out to actually implement this thing, and our overall goal was to make it eventually available for use in a production environment. And to go along with that, we had to design it, with the idea in mind that this thing is actually going to be attacked on purpose. So it has to be performant and scalable and fault tolerant, and it has to support the needs of actual deployment environments. So what we did is we took that Gatekeeper server and we broke down the architecture into different, what we call functional blocks, which are essentially microservices. And so all of the different pieces of functionality are broken off into their own blocks, some of which can be scaled up. So for example, the main data plane operations that take place in a Gatekeeper server is that packets from clients come in through the front interface, and one or more instances of this Gatekeeper block or GK block process that traffic, apply rate limits or drop packets, and forward them out the back interface towards the destination AS. But there's also all of these other sort of operationally required blocks. So we have a link layer support, for example, to take care of ARP and neighbor discovery and IPv6, where we actually implemented these protocols ourselves. Same thing with control plane support, right? We need to be able to leverage that BGP speaker and also to send routes back and forth between the BGP speaker and the Gatekeeper software. So we have all of these different blocks to support those kind of things. And one of the techniques that we needed to take advantage of was scalability, of course, and we figured out a way to scale Gatekeeper in 4 different ways. As I just mentioned, we had that modular implementation of those blocks, right? So that we could scale up the data plane processing, for example, without touching the control plane stuff, right? Each one of those GK blocks, those GK instances, we can just assign more threads to it. We also have support for bonded devices to linearly scale network capacity. Gatekeeper and Grantor servers are both horizontally scalable. So within a VP, you could have a set of Gatekeeper servers, and incoming traffic is load balanced to those servers. Same thing in the destination AS, where you could have multiple Grantors. And then, of course, multiple vantage points throughout the internet. And in terms of performance considerations, we thought very deep and very hard about what kind of software and hardware techniques that we were going to use for optimizing packet processing. We ended up choosing DPDK, which as our packet processing framework, because this performs kernel bypass. So we're avoiding a lot of the Linux kernel networking stack, which in general is very useful, but there's also a lot of bloat in there, right? It supports a lot of different applications and protocols and services. And that takes a lot of time that we don't really have for a DDoS mitigation system. So we had to implement a lot of our own stuff on top of DPDK, right? As I mentioned, ARP handling. We had to implement a routing table. We had to implement the IPv6 version of ARP. We also use some pretty well-known techniques in software for processing packets, such as batching, prefetching. We made use of a lot of branch prediction just to try to get little speed ups wherever we could. We took advantage of things like non-uniform memory access and also hardware offloading capabilities as well, right? We used ether type and n-tuple filters to map control plane packets to blocks. In other words, when ARP packets come in or when BGP packets come in, we can map those directly to those control plane blocks that handle it, instead of having to receive everything by one sort of receiving thread and distribute it. Receive side scaling is a similar notion of that. It gives us the ability to spread incoming data plane traffic between multiple instances of our data plane module. There's a lot that you could talk about here, and I'm sure a lot of things that I've even forgotten in the 5 years that we've been implementing this. But for more information about this kind of stuff, you can see Chaobin's dissertation, High Performance Software Packet Processing. And in order to have this thing be deployable, we needed it to meet certain operational requirements as well, right? So we needed to have things like VLAN tagging, rate limiting logging, support for existing control plane tools, like this routing daemon, for example, and a runtime configuration client. So as I said, this was a multi-year effort, and we're really just now coming to the point where we can start to evaluate Gatekeeper. And so I've done it along a few different axes. Just sort of basic functionality, can Gatekeeper mitigate attacks? I also looked into the richness of the policies that Grantor servers can install at Gatekeeper and how these various policies affect Gatekeeper's ability to do the mitigation. We've done some stress testing, and we've also thought about cost, right? How much does Gatekeeper cost and what do you get for it? So I set up an evaluation on Amazon Web Services on their EC2 service, where I had a bunch of different attackers, 16,000 flows, attacking a single destination server. At the same time, I tried to have one legitimate client try to upload a 20 kilobyte file. And of course, it's going to be totally inundated by all of this attack traffic, right? All of this flooding traffic. So when that happens, when you don't have any defensive system at all, right? Naturally, as the strength of the attack increases, the time that it's going to take this legitimate client to transfer this file is also going to increase. Right? This is even a log scale y-axis, and even at 5 gigabits per second, it's taking around 100 seconds just to transfer this file. So what would happen if we put Gatekeeper in front of this now? So if I put Gatekeeper in front of it and use a policy decision from grantor that essentially just applies the same rate to all flows, right? It's not trying to differentiate between legitimate and attack. It just says for every flow, only allow 16 kilobits per second. Then it's narrowing, right, these bands down. And now the legitimate client can actually obtain a decent amount of service. In fact, enough so that it can transfer the file. It might take 20 seconds or so because this rate limit is fairly low. But you can see here that this line, no matter what the attack strength is, Gatekeeper can handle it, right? Up all the way up through 10 gigabits per second. It essentially neutralizes the attack and allows the legitimate client to send the file. And you could play this same game at different rate limits, right? So I showed what it would be at 16 kilobits per second. But then we thought about, okay, what would happen if you doubled that rate? You're going to be letting the legitimate client send their file quicker, but you're also going to be letting more attack traffic in. At least at this rate and in this setup, it didn't really matter, right? The legitimate client was able to send its file through without any significant effects. And again, even when we doubled that to 64 kilobits per second. So the overall lesson here is that even just using basic rate limiting policies, Gatekeeper can handle up to 10 gigabits per second in mitigating attack traffic. We'll take this basic policy enforcement and kind of spice it up a little bit with more sophisticated policies in a bit. Before we do that, though, we also just looked at sort of stress testing Gatekeeper and thinking about packet throughput sort of under worst case conditions. So this time, instead of just having 16,000 flows, which is fairly low in the grand scheme of things, we used random source addresses so that now basically every packet that's coming in represents a new flow. And so our flow table, sort of the critical data structure that's mapping to decide what to do with packets, is constantly full, right? It's constantly churning with new flows being added, flows being deleted to make more room. And to make things even worse, we used a minimum packet size, only 64 bytes. And we ran it on bare metal hardware. And we found that for certain table sizes and for certain numbers of threads, and L-core is just a DPDK term for thread, you can achieve close to 10 million packets per second. The packet generator we were using was run on the same hardware as Gatekeeper, so it was obviously taking up a lot of CPU and memory as well. So this would probably be even slightly more, but the takeaway here is that there's a sweet spot for your table size and for the number of L-cores that you dedicate to the data plane processing to maximize the throughput, even under these worst case conditions. We thought about cost.
Cody, sorry, quick question. So in this case here, you are, because you have so many flows and there's only one packet per flow, I'm assuming you are not protecting any longer the legitimate traffic, right? Is it still, it gets overwhelmed, right?
Yeah, we're not even measuring legitimate traffic here. This is just seeing how fast can Gatekeeper handle all of this in this kind of high intensity environment. There's
okay,
no,
but you didn't measure, you didn't evaluate how much protection you can get if you have very short flows, attack flows, like you have in this case.
no, not in terms of like what benefit a legitimate application would get. No.
Okay, thanks.
Mm-hmm. So we have some estimates for how much Gatekeeper would actually cost. And we can also pull quotes from public materials a lot of this information is kind of kept secret in the industry or sensitive. So a lot of it is estimates and sort of back of the envelope evaluations. But we thought about what the cost would be to defend basically one of the largest attacks that's ever been seen, a 2.3 terabit attack. For Gatekeeper, we figured that with 23 vantage points, each having a capacity of 100 gigabits per second, that the monthly cost per vantage point would be around $5,000. Okay, and this is based on conversations with industry partners, and we think that would be fairly conservative. So total, that would be $1.3 million per year, which is a lot. But when you think about attacks like that which happened on the popular blog Krebs on Security, Brian Krebs is a network security journalist with a very popular security blog. That suffered a 620 gigabit Mirai attack in 2016, an attack that was so damaging that Akamai, who was providing pro bono protection for him as a journalist, revoked that protection and said that, if this kind of thing is sustained, then the cost of that attack could be millions, just for that one event. So comparing the two, this cost of over $1 million per year versus the cost of multiple millions of dollars for a single attack, Gatekeeper stands up pretty well. But we could also think about the fact that most of these attacks are not that big, right? 99% of DDoS attacks are less than 20 gigabits. And our estimate for that is like $12,000 per year. And a confidential estimate for a service that was offered to one of the operators that we've been in discussions with was around twice that. So it's at least in the ballpark, if not cheaper than some of the commercially available protections available. Okay, so I've spoken about the architecture in general and evaluated some basic parts of it, but really the richness of Gatekeeper comes in through the policies that can be installed. So Grantor is making decisions about which flows should be granted, but it's also making decisions about how those flows should be processed at Gatekeeper. So there's really two sides to this policy that we need to be aware of, right? There's what we call policy decision programs at Grantor, which we implemented in Lua. Those policy decision programs receive requests, right? The first packet of a new flow, and they map those flows to policy decisions. The policy decision itself contains a policy enforcement program that is then installed at Gatekeeper. And those policy enforcement programs are implemented in eBPF, Berkeley packet filters. So in the simplest case, these programs just drop or rate limit, right? That's all Gatekeeper was originally designed to do. But we realized that we can inspect the headers of every packet, right? We can look at the transport layer headers, look at the port numbers, for example, and figure out, should you really be sending to this port? We could look at even further, right? We could look at application layer headers or different fields in the IP headers. And this is happening on a per packet basis. With these programs, each flow is given 512 bytes of program state. So every flow in your system, you can have some state associated with it alongside this program to determine whether and how to rate limit the traffic. So the question is, what can you do with this? What can you do with this state and this programmability? Where we last left off talking about basic policies, we just had this kind of static 16 kilobit per second per flow rule that was applied for every flow. Well, what if we kept increasing it? We had increased it a little bit. What if we increased it all the way up to something like 256 kilobits per second per flow? At that rate, the amount of attack traffic that's coming through is sufficient to kind of drive up the legitimate client's file transfer time. It's no longer that nice flat line, right? The attack strength is really driving it up above 100 seconds. So instead of just applying that flat rate per flow, let's make the policy a little bit richer and say, once this little gray box goes away, apply a negative bandwidth for flows that misbehave. In other words, when flows send at more than their allotted rate, they start to accumulate negative bandwidth, or bandwidth debt. And as long as that bandwidth allotment is negative, all of their packets are going to be dropped. So as soon as we now apply this negative bandwidth addition, all of these attack flows, all of their traffic is going to start to be dropped, and only the legitimate client is going to be able to send. So with this, the second version of this policy in place with the negative bandwidth, once those attackers get to a certain point and they start sending, more than their allotted rate, the transfer time for the legitimate client plummets, because it's really the only one that's being able to send. And I'm pausing for dramatic effect because I think that's a really nice illustration of sort of the richness of these policies. Same thing happens at only 128 kilobytes, right? With just a flat rate, the attack is going to be somewhat successful and going to drive up the file transfer time up to, maybe 40 seconds. But if you punish flows that go beyond that rate, this green line here, the legitimate client transfer time is going to stay fairly low.
Cody, quick question.
Sure.
Given the pause, have you tried? So I understand you are rate limiting, and then packets will go into the same queue, output buffer, or are you using any kind of per flow scheduling there? Or can you isolate flows somehow so that you are guaranteed your 256K regardless of what others are doing, like weighted fair queuing scheduler or some kind of scheduler like that?
At the moment, no, but if we're looking at situations where, when Gatekeeper is overwhelmed, how can you sort of orchestrate flows so that it's fair between them? At the moment, it doesn't exist. There's other cool things you can do with the expressiveness of these policies. For example, you could implement port knocking. Port knocking is it's a lightweight authentication mechanism where instead of handing the service like a client TLS certificate proving who you are cryptographically, you can prove who you are through a series of probes to certain ports. So the policy decision from grantor might say something like, only allow traffic from flows that follow the port knocking pattern, port 1111, 2222, 3333. And so if none of the client traffic implements that port knocking sequence, then Gatekeeper is essentially a firewall and is going to drop all of that traffic. But if you first probe the server with this specific sequence of knocks, then you'll be able to actually send and have your data transmitted. And the exact way of, getting this port knocking sequence to clients, like through some sort of out-of-band mechanism is outside of the scope of what we're thinking here. But it's just another way of thinking about these policies and the state that you can keep and the way you can differentiate clients, legitimate clients and attackers based on that state that we think is really powerful. So there's a lot more in the thesis, denying admission if its traffic is headed for ports that aren't really in use, or being able to detect amplification tax, using these policy enforcement programs, disabling traceroute, all sorts of different things that are given in this policy toolkit. Okay, so in the few minutes I have left, I just want to talk about looking to the future now and thinking about the next generation attacks and what Gatekeeper might be able to do for combating those. As we mentioned before, there are three major shifts occurring in the internet ecosystem, IoT, 5G, and IPv6. And the consequence of this is that attackers will be more powerful than ever, just as the internet architecture and the infrastructure undergo a major transition. And these trends favor large-scale links, large-scale link attacks like Crossfire. Right? There's a much bigger pool of bots, and the infrastructure for the links that they're targeting, as they're transitioning maybe to IPv6 only infrastructure, might not be as well provisioned. So I'm going to go through a very brief setup of a Crossfire attack and see how Gatekeeper kind of neutralizes the assumptions that Crossfire is making. In a Crossfire attack, the adversary selects a set of bots in the internet, these red circles here, and targets a set of decoy servers that are geographically close to, but not necessarily within a target area, right? This is the victim area. And the adversary takes those bots and sends traceroute probes from the botnet to the decoy servers, essentially building a link map of all of the links around this target area. The adversary can measure, which of these links around this target area are carrying the highest proportion of traffic of flows, and pick those as target links. So those target links are going to be the locus of attacks. And then to maintain attack persistence, the adversary can rotate this set of target links between disjoint sets of target links in order to evade mitigating maneuvers, for example. So this is an as of yet unsolved problem, and it's partially because all of the previous solutions in this space are either point solutions that kind of make simplifying assumptions. For example, assuming that those target links are actually within the target area. In the classic version of the attack, that's not the case because you don't have visibility into where the attack's happening. Or the solutions assume that you can cooperate between different networks so that you can say, I'm seeing this really high link utilization. Is it leading to an attack? Right? You can kind of work together to figure it out. Or these solutions require a complete restructuring of the internet, such as to do a complete bandwidth reservation service that, at least in the current internet, is not really feasible. But Gatekeeper neutralizes sort of all of the architectural advantages that Crossfire has. It does so in three different ways: by, in that first phase, diluting the construction of all of those of that link map. It provides path diversity to circumvent the target links that the adversary finds, and it also enables a moving target defense. There's a lot of details here and a lot of techniques, but I'm really only going to focus on this second one, the ability of Gatekeeper to provide path diversity to get around these target links. So to actually figure this out, we conducted a real-world measurement study to build a Crossfire link map. We picked traceroute servers distributed throughout the internet using looking glass nodes. So those are essentially our bots. And we picked a target area just being the universities around the Boston area. And we took all of these traceroute servers and sent a bunch of traceroute probes to maybe 100 different publicly available servers, between these universities, and built the persistent link map and chose a bunch of target links, based on the flow density. And we wanted to compare, our link map to what was constructed in some previous work. And the key metric of success of a Crossfire attack is the degradation ratio. In other words, the fraction of paths to the target area that's crossing a target link. If you can get most of your paths to the target area crossing a target link, right, the links that are being attacked, then you're going to be doing a pretty good job of cutting off service to that target area. So we found that in all of our trace route probes to the target area, it only takes around 10 target links to capture 75% of the paths. In other words, to force 75% of the paths through a target link. If you had chosen 20 target links and attacked those, then close to 90% of paths to the target area would be crossing target links. So then we asked, but in Gatekeeper, all of the traffic is forwarded through a set of vantage points. Right? It's not going directly to the target area. So we wondered whether the paths from clients would still be crossing those target links, or if by virtue of first going through a vantage point, whether the path diversity would be different enough to avoid those target links. So we used 6 Amazon cloud nodes in different world regions as a representative vantage point. We didn't actually deploy Gatekeeper. We just used those cloud nodes as representative vantage points as part of the measurement study. And this is what we found. We used a United States vantage point, a couple in Europe, Australia, India, and Brazil. And we found that for some of these vantage points, there is a lot of overlap in paths from the vantage point to the target area, right? They are crossing those target links. For example, it only takes a couple of target links in order for 60% of the paths from one of the European VPs to cross a target link. But for many others, there's very little overlap or no overlap at all. So for the United States and for India, none of the paths that came from their vantage points crossed target links, right, in the link map that we constructed. So you can't even really see the US points down here because it's just 0 the entire way. So in other words, the takeaway here is that cloud paths can be fairly independent from the internet paths, which is a well-known result in general. But the effect here is that it might be a good technique for neutralizing Crossfire attacks because these paths might not cross target links. We drilled down into what happens specifically in the case of 20 target links. What's sort of the link anatomy of what's going on at that point? And so we plotted all of the potential links by their flow density, right? The number of flows crossing through these links. And we've highlighted here the target links that were selected out of all the possible links. We picked 20 of them, but we only show the first 12 for space reasons. And so for paths that come from this European vantage point in Frankfurt, 25% of the paths go through a target link, but they all go through this one target link here. For Australia, 2% of the paths go through target links, right? So just 1 out of the 48 that we measured go through this link here. None of the paths from India go through target links, and a fairly high percentage, 60%, go through target links from a vantage point in Brazil. But the target link that they go through is sort of a low value target link. All right, it's even off the chart here. So in other words, adversaries have to be, they're not necessarily capturing traffic with these high value target links. They have to be paying for larger and larger attack to be able to inundate all of these links. And then we also looked at the version of the attack where you rotate between sets of target links. So if you have 3 sets of 10 target links that are all independent from each other and that the adversary rotates between, you basically get the same effect. For all of the flows coming from United States VP, if you just look at the paths going through the first set, none of the paths cross target links. 17% of the paths from the United States VP go through target links in set 2, but none go through target links in set 3. And we observed that broadly with other vantage points too. So the key takeaway from this measurement study was that when Gatekeeper is deployed in cloud environments like Amazon, it can leverage the independence of cloud paths to circumvent Crossfire target links. So to summarize the talk as a whole, we've put into place a deployable realization of a network capability system using IXPs and clouds. In effect, putting a connection-oriented network layer into practice at last. We're using the enforcement of expressive policies with programs instead of declarative rules, which is enabling this rich set of algorithms and actions to apply per flow. And we're providing opportunities to mitigate next-generation attacks, such as by leveraging architectural and topological advantages. And just a note, I've talked this entire time about the deployability of this thing, and it actually is being deployed by 2 different networks. So Digerati has been sort of our partner from the beginning, and they were looking for a fairly small and affordable deployment, but a comprehensive one too, something like 10 gigabits per second. What we didn't expect was to basically, this other network reached out to us, which is mail.ru, which is a Russian social media and ISP giant, really. They were looking for like massively scalable DDoS protection. And they're starting with a Gatekeeper deployment for 1 terabit per second protection, which, I mean, there's only been a handful of attacks that are more than that. So the value here is that you're getting a comprehensive and affordable solution, but it's also scalable. So it's suitable for a range of different networks and needs. So thank you to everyone that's helped me along the way. There's far too many to name here, but you know who you are. So thank you very much. I appreciate all of your help. And with that, I'd be happy to take questions.
Okay, well, first of all, if you can unmute, let's show our appreciation to Cody. Okay.
Thank you.
And I would open the floor to anybody. I don't think you need to raise your hand. If you just speak up, I think we can use exponential backoff or something to. Sorry, I just came from teaching networking, so go ahead, anyone who wants to.
Cody, a quick question about scalability.
Yep.
You said you can horizontally scale the services, the Gatekeeper services. Can you say a little bit more about that? I mean, can I scale across different machines, or you're talking about within the same machine? You mentioned threads, I guess.
Yeah.
Can I scale across different machines? That's my question, I guess.
Yeah, definitely. So within a vantage point, you can have multiple Gatekeeper servers and load balance flows to those different servers. So the same flow is always getting load balanced to the same server. And within that server, you can also scale up the number of threads, essentially. Yeah.
Okay, so you can put a load balancer in front of it, in front of multiple gatekeepers.
Right. Yep.
All right. And when you talked about the cloud path and they don't cross target links, have you looked at actually adapting then the source vantage points so I make sure that cloud path are actually, I can control the cloud path, or I can actually run the cloud path through multiple vantage points that I have, I guess, right? So I can have an overlay path Is that a possibility, or is this too complicated?
It could be a possibility. I'm not sure if it meshes with the Gatekeeper architecture. So far, it's more just a feasibility study of the effect of the independence of these paths on getting around the attack. And we think that if Gatekeeper were deployed in the cloud, that we could take advantage of that fact. But yeah, the exact mechanism we haven't really spec'd out yet.
Mm. So I'm guessing you are assuming always when you mention things about the cost and the very high cost in terms of dollar cost, I guess. Did you think about other ways to, let's say, dynamically instantiate these cloud Gatekeeper services as a function of attack traffic or the demand from attack traffic, I guess?
Yes, actually.
Yeah,
that was one of the topics I glossed over for time. But you could have sort of a moving target defense, especially with the agility of the cloud, where you can bootstrap like another VP in a fairly short amount of time and dilute the attack traffic even more. Yeah.
Okay.
Cody, can I just ask some really basic questions?
Sure.
To what extent is the Gatekeeper device a sort of superset of just a software-defined networking switch? Could you have used the SDN switch for the key functions in Gatekeeper?
There's definitely some parallels here between SDN and Gatekeeper, especially if you think about the centralized authority of grantor. That's more like an SDN controller. Yeah, you can think of Gatekeeper as the analog to an SDN switch in that case, but I'm not sure you could get the same, like, the actions that we're applying are essentially programs, and I'm not sure that capability currently exists, at least in SDN, but it's analogous in applying generic actions to flows. Yeah.
When you talk about deployment, what's you've got, I guess, one deployment and one that's in the process of being deployed, right? What's actually being deployed from? In other words, is it the architecture generally, or is it boxes that you built and programmed, or what do you mean when you say it's been deployed?
So we didn't design any special hardware. For example, the Didgeridoo deployment is they're going to put just a basic set of networking gear into a Brazilian internet exchange point. So that consists of just your router to connect to the fabric of the IXP, and then they're going to have a Gatekeeper server associated with that. So it's really just a server and a switch, a server and a router dropped into an IXP.
And what about the management?
Architecturally, they're deploying the architecture as well. They're going to be using your scheme for address announcements, packet encapsulation.
Yep, all of that. At least in the Didgeridoo case, it's not yet going to be a global scale deployment. That the network that they're protecting is very geographically close to the vantage point. As far as I know, it's only one vantage point. So it's not as distributed as it was presented here, but it's the same architecture fundamentally.
Well, just so I understand, I mean, I sort of thought that the oh, I see. It's still valid to run this with just a single vantage point.
Right.
The Anycast component isn't really there, but other than that.
Right. Yeah.
It logically pushes the protection further away from the
Right.
target.
And creates a protection point. Yeah. Right.
I mean, I think the architectural sauce is really in the Anycast version, but yes.
Yeah.
What about the mail.ru deployment? I mean, they've been pretty cagey, Cody. I know they're using the software, but do we know anything about what their deployment looks like?
I don't know too much about it. Michelle has had more conversations with them. I'm not sure if he knows either.
They are working on the deployment, but they have such a large network. Going to the one thing that they announced, they have more than 100 terabits of bandwidth interconnecting them to the rest of the world. So they don't really need to rely on internet exchange because they already have more links than they can use. So what they are doing to deploy Gatekeeper, essentially they have this Gatekeeper service spread throughout the network, and they have a system to monitor all the links that they have, and they using I don't remember the exact name of the protocol, but it's a popular flow spec. So they decide which network prefix are being attacked and redirect all the traffic of that prefix to over Gatekeeper, and from there the traffic go to the destination. Everything is done inside of their own network. They don't need to rely on any external partner, but that's very unusual. Their network is just too big.
Any further questions?
Yeah, so I had a couple of quick questions, Cody, but before that, really nice work. Well done.
Thank you.
So some of the optimizations you use to improve scalability and performance of Gatekeeper, are they are those optimizations specific to Gatekeeper, or they would apply to any like software-based IDS, or did you use any like Gatekeeper-specific optimizations?
Most of them are broadly applicable and well known. There's one technique that I didn't present here, but that we've considered using for Gatekeeper and have a implementation of in the works, and that's the use of coroutines. Xiaobin is more of an expert on this than I am, but as far as I understand, coroutines have been used in distributed systems or systems in general, but not for the context of packet processing. So we're still trying to fully implement that and evaluate it, but most other things are general techniques.
Okay. And in terms of like scoping of your work and like the target networks and the target potentially applications, I got the impression that you are mostly targeting ISPs as your clients, right? But would this apply to, let's say, large service providers too, like Google, Amazon? Would they have any incentive to use something like this, or they already have like geographically distributed infrastructure, and they would probably not be a good fit for this? So this is like one part. The second part is about applications. Would like latency sensitive applications, applications with short flows, would those be amenable to this kind of a solution?
Okay, so for the first question, it's true that we mainly think about in terms of like small and medium-sized networks and ISPs, just because those are the ones that can't afford to do it themselves in the traditional way or pay others. I think it still could be used for like big content providers, especially because they already have the vantage point infrastructure, right? They already have the POPs, the points of presence, to be able to do it. And I think they could still gain benefit from the architecture, right? From the centralization of like the policy distribution and the richness of the policies. I think there would be plenty to gain for them. In terms of your second question was whether it would be beneficial or work for shorter flows.
Shorter, like latency sensitive flows, as in would the connection setup overhead be too much? Would the rate limiting be too costly in terms of the added latency for them?
It could be one of the benefits that Gatekeeper has is that it's applying the policy upstream per packet. So if the application is latency sensitive, but it's on a well-known port and the policy is aware of that, it could allow packets sent for that application specifically to be at a higher rate than the rest of the traffic, for example. So it could be tuned to sort of support latency sensitive applications.
Okay, great, thanks. I'm done.
Keeping in mind that I know John has a time limit, maybe unless there are further questions, we can go into our closed session.